Heat calculations, M1, Mr. Gary, course science. Heat, otherwise known as Q, transfer of energy between objects due to a temperature difference. It flows from the higher temperature object to the lower temperature object. Now, if system 1 is T1, like a square cube, and the surroundings around it is system 2, T2, if the cube heat is higher than the surrounding heat, it's exothermic, meaning the heat will leave from the cube to its surroundings. It will give off heat. Exo means exit. If the system is reversed, where the cube, T1, is cold and the surroundings are hot, T1 is less than T2, the system is endothermic, because then the heat will go into the system T1. Be aware of your reference point, because if you use T2 as your reference point, that changes the whole situation. But we'll talk about the cube, T1, and the surroundings is T2. Calorimetry, the measure of heat energy. A device that's used to measure it is called a calorimeter. Specific heat capacity is the amount of heat needed to raise temperature of 1 gram of a substance 1 degree Celsius, or 1 degree Kelvin. The same thing. Be careful, sometimes specific heat is in the form of, instead of it being 1 gram, it's 1 kilogram. Be aware of your units. This is only usable within a state of matter, liquid or gas, solid. If you have energy changes involving melting, freezing, boiling, condensing, this is known as the heat of fusion, is melting or freezing, and the heat of vaporization is boiling or condensing. There are no temperature changes. There are no temperature changes during a phase change. This is a special circumstance. Remember our temperature graphs? That's what we're referring to. There is energy being exchanged there, but it's very specific. It's very unique to that situation. Here are various specific heat capacities. Note it's joules per Kelvin, gram. Metals that do not generally require much heat to heat them up, gold, silver, copper, iron, aluminum, i.e., means for example, I don't know why it's an I and an E, they heat up easily. Water needs a lot of heat before it can heat up 1 gram. Liquid, solid, gas. So liquid form of water has the highest heat capacity. We can find the heat a substance loses or gains using, and for purposes we call it Q, which is the heat energy, equals mc delta T. This is within a given state of matter. And Q equals mass times delta H, which is the change in heat. During a phase change or a change between two states of matter. So Q is equal to heat in joules, M equals mass, your substance in grams. The specific heat is a number, the amount of heat required to raise 1 gram of substance 1 degree Celsius or Kelvin. Delta T is a change in temperature. The little triangle is known as delta, and normally it denotes change. You should know this from math. Delta H is the change, is the heat of fusion or vaporization. In our temperature curve, which we'll learn later, the red lines denote places where the heat is going to be calculated using the formula mass times delta H, which is the heat of fusion and the heat of vaporization. For the blue parts of the graph, S, L, and G, we will use Q equals mc delta T. And that's for our heating curve problems. Remember, when it goes from solid to gas, you have a positive change in heat, an increase, and when it goes from gas to liquid, you have a negative change in heat. Using heat capacities, Q equals mc delta T. Q is in joules, the mass is in grams, C is the specific heat, the amount of energy required to raise 1 gram of a substance 1 degree Celsius, times the change in temperature, delta T. When you cancel out all the units, Q equals M cat. Yay! Let's do a sample problem. Find the amount of heat. So you have a 500 gram cube of lead. It's heated from 25 degrees to 75 degrees. How much energy was required to heat the lead? The specific heat of lead is equal to raise 1 gram of lead 1 degree Celsius would require 0.129 joules per gram per degree Celsius. Label your variables. So what do we know? Mass is 500 grams. C, which is the specific heat, is given to you, 0.129 joules per gram per degree Celsius. Delta T, you have to calculate. T final, which is 75 degrees. T initial is 25 degrees. Subtract them, you get 50. And normally delta T, we keep it as a positive function. Plug these values into the specific heat equation from above. Q equals mc delta T. And then after that, it's just math. You can set the problem up as so, and then solve it. But I'm very happy to set the problem up as so. Solving is just a matter of math. It took 3,225 joules of energy to heat the lead cube from 25 degrees Celsius to 75 degrees Celsius. So this problem is a specific heat, the amount of heat problem. And they ask you specifically in the problem, how much energy was required to heat the lead. So they are asking you how much energy. So that's Q. Therefore, you know you're going to try Q equals mc delta T. It's always important to look at the word problem and see what they're asking. What's missing? The second type of problem we're going to do is find the specific heat. You have a 25 gram metal ball. It's heated 200 degrees Celsius with 2,330 joules of energy. What is the specific heat of the metal? What do we know? Mass is 25 grams. Delta T is 200 because it's heated 200 degrees Celsius. And Q equals 233. What's missing? C is missing, so we solve for T. Q equals mc delta T. What's missing? The C. So now we solve for C, and it becomes a math problem. 25 times 200 is 5,000. Divide both sides by 5,000 grams. So C is equal to 2,330 joules divided by 5,000 grams per degree Celsius. And the answer becomes C equals 0.466 joules per gram per degree Celsius times degree Celsius. That's specific heat.